In this video, we're going to define a manifold without boundary. Before getting into the technical definition, let's just do some examples of what a manifold should be. For instance, a curve is going to be a one-manifold. And what's special about this curve C? Well, if you take a point, say P, in C, the points nearby look like a line. So if I take around P, there's some neighborhood containing P, let's call it V, such that this piece looks like a straight line. And one way to describe it is that there's a way to map an open interval. So here's R1. There's a way to map an open interval, say U, in a continuous way onto V. There's some map alpha that maps U onto V. So this would be a continuous one-to-one and onto map. So, roughly speaking, a one-manifold is a set such that for every point in that set, there exists some open interval in R and an open interval V and a map alpha that's continuous that maps U onto V in a one-to-one fashion. That's roughly the idea of a manifold, of a one-manifold. And that's also roughly the idea of a two-manifold also. So a two-manifold is like a surface. So let's say you have a sphere. Well, for a sphere, you have the same story. If you take a point P on the sphere, there's some open set in S, let's call that set V, and there's a map from a subset, an open subset U in R2 there's some open set U in R2 and a map alpha that maps U onto V in a continuous one-to-one fashion. So it's a continuous one-to-one and onto map. And we can do this for every point on the surface. So a curve is a lot like a surface, and a curve, this curve we'll see is a one-manifold. So notice that this alpha is mapping from an open set in R1, and a sphere is going to be an example of a two-manifold. There's a map alpha from an open set in R2. So with this in mind, let's get to the technical definition. So let's say that K is some positive integer. We're going to define a K-manifold. So suppose that M is a subset in Rn, and we give M the topology induced by Rn. And so suppose that M is a subset with this topology induced by Rn with the following property. For every P in M, there is a set V containing P that is open in M. So there's some open set that contains P, and this is an open set in M. A set U open in RK, and a continuous map alpha from U onto V. So this is a one-to-one and onto map. Okay, it's a one-to-one onto map from U to V, such that alpha is of class C infinity. So this is the smoothness condition. This means that it has it's differentiable and it has continuous partial derivatives of all orders. This is, we technically don't need this condition, but it just makes things easier to work with. So we're just going to work with C infinity maps. So alpha is C infinity, and alpha inverse, which is defined because alpha is a one-to-one map from U onto V. So alpha inverse is a map from V to U. It's a one-to-one onto map from V to U. This inverse map needs to be continuous. And then the third condition is that the derivative of alpha has rank k. So at each x in U, d alpha has rank k. This is for each x in U. So if you have something like this, then M is called a smooth K-manifold without boundary. Then M is called a smooth K-manifold without boundary. We'll talk about manifolds with boundary later, but for now, let's just work with manifolds without boundary. And this map alpha, the map alpha is called a coordinate patch on M about P. So roughly speaking, what this definition is saying, to go back to our examples, is that for every point on the surface, or on the manifold in general, there is some open set V. So this is a set that's open in the topology of M, okay, and an open set U in RK, and the map alpha that maps U onto V in a continuous way such that alpha is differentiable and has continuous derivatives, continuous partial derivatives of all orders. So it's a nice smooth map, okay, and the inverse map needs to be continuous, and the derivative needs to have rank k, and when you have that, then you have a K-manifold. So every point of your manifold, in some sense, can be covered by coordinate patches. Right? You have these coordinate patches in every single point of your manifold. So if you have a point here, you have a set like this, and then some other open set in R2 that maps onto this patch, onto this set V, that's a coordinate patch, and then you think of this manifold, or well, in this example, this surface, as just being covered by these patches. covered by all these maps alpha. So that's the idea. And then the same thing can be said for a curve. Okay, each point that has some open set that's covered by some smooth map alpha. So that's the idea behind the definition. And in the next video, we're going to look at some examples and we're going to explore these properties. One is pretty easy to understand, but why do we require 2 and 3? We'll see that in the examples in the next video. Thanks.